Hello guys, so this is question number 20 of engineering thermodynamics that appeared in civil services means examination of 2003, and this is of 30 marks. So let us read the question. Now air at 17 degrees Celsius and 1.1 bar occupies 0.05 meter cube. The air is first heated at constant volume until the pressure is 4.4 bar and then cooled at constant pressure back to original temperature. Calculate the net heat transfer to or from the air and the net entropy change. The value of Cp is given, the value of Cv is given. So let us solve. So first of all, we have to make a PV diagram always in a thermodynamics question. So this is a major requirement to solve a thermodynamics question. So given is state 1. So it is heated at a constant volume. So if it is heated, then the pressure will increase. Now if it is cooled at a constant pressure to its original temperature. So it is cooled at this temperature. So its volume should decrease. So it should go like this. So now this is stage 2. So it should go till stage 3. So this is the process 1 to 2, 2 to 3. So process 1, stage 1. At stage 1 we have get the value of P, that is equals to P1 is equals to 1.1 bar. T1 is equals to 17 degrees Celsius and V1 is equals to 0.05 meter cube. Now from these three values we can calculate what should be the mass here, or rather we know that this is a constant volume process, so V2 should also be equal to V1. So we should write V2 is equal to V1 is equals to 0.05 meter cube. And now using the ideal gas equation, P1 by T1 is equals to P2 by T2. We can get the value of T2. So T2 is equals to P2 divided by P1 multiplied by T1. Plugging in the values here, we get T2 is equals to 4.4 divided by 1.1 multiplied by T1, that is 290 Kelvin. We can get the value of T2. This comes out to be 1160 Kelvin. So we have calculated the value T2, and as we know, we have calculated the value of T2 and value of P2 is known to us, that is equals to 4.4 bar, and the value of V2 is also known to us, that is equals to 0.05 meter cube. Now again, using the ideal gas relation at a constant pressure process, we know that V2 by T2 should be equal to V1 by V3 by T3. And as we know that T3 is equals to the value of T1, that is given in the question, given T3 is equals to T1. We substitute the value to get the value of V3. Now V3 is given by V2 multiplied by T3 divided by T2. Now we put the values here, we get 0.05 multiplied by T3. Now what is the value of T3? T3 is equals to T1, that is equals to 290 Kelvin. And what is the value of T2? The value of T2 is 1160. So here we get the value of V3, that is equals to 0.0125. Now we have calculated the P1, V1, T1 at all the three stages, and the value of R for this air is given by Cp minus Cv which is equals to 1.005 minus 0.718, that is equals to 0.287 kilojoule per kilogram Kelvin. Now we have got the value of R also. So using the value of temperature at 1, volume at 1 and pressure at 1, we can calculate the mass of the gas in the system. Hence, mass M is equals to P1V1 by R into T1. This comes out to be 1.1 into 10 to the power 5 into 0.05 meter cube divided by 0.287 into 10 to the power 3 joule per kilogram Kelvin into 290. Now this comes out to a 0.0661 kilogram. Now we have calculated the value of M. Now we have to calculate the first thing, that is the net heat transferred to or from the gas. So heat transfer from stage 1 to 2 is a constant value volume process. So Q1 to 2 is equals to mCp multiplied by T2 minus T1, that is given by 0.0661 into 0.718 into T2. What is the value of T2 is 1160 minus T1, that is 290. We get the value as 41.28 kilojoules. Similarly, the value of Q2 to 3 is equals to mCp multiplied by T2, or rather T3 minus T2, is equals to 0.066 into 1.005 into 290 minus 1160. Now this comes out to be minus of 57.79 kilojoules. Now we have calculated the value of Q12 and Q23. So net heat transfer is the summation of these. So net heat transfer is equals to Q122 plus Q223. Now this comes out to be 41.28 minus 57.79, and that is equals to minus 16.51 kilojoules. So first question is now solved. Now second question, we have to find the total entropy change here. So delta S from 1 to 2 is equals to the mass multiplied by Cp ln T2 by T1 minus R ln P2 by P1. Now plugging in the values here, we can just find the value of delta S 0.066 multiplied by 1.005 into ln 1160 divided by 290 minus 0.287 into ln 4.4 divided by 1.1. Now this comes out to be 0.0658 kilojoule per Kelvin. Similarly, we can calculate delta S 2 to 3 which comes out to be m into Cp ln T3 by T2 minus R ln P3 by P2 is equals to 0.066 into 1.005 into ln T3 is 290 divided by 1160, and because P3 is equals to P2, so this term comes out to be 0, and we get the value of delta S from 2 to 3 as equals to minus 0.0921 kilojoule per Kelvin. And now when we add the total entropy, we get net entropy change as delta S1 plus delta S2, 1 to 2 plus 2 to 3 is equals to minus 26.3 joule per Kelvin. So this has to be noted. The unit is joule per Kelvin, and here the unit is kilojoule per Kelvin. So because this quantity comes out to be very less, we have used joule per Kelvin here. So we have solved the two questions. So thanks for watching. See you next time.